Okay, so good morning again. I'll be talking to you about quantum geometry and related phenomena in 2D materials using first principles theory. There are two parts in this talk. In the first part, I will introduce to you a new class of spectroscopies that we are proposing based on quantum geometry and demonstrate these with vibrational spectroscopy in 2D materials. And this work was done by Bhuvaneshwari, who is sitting behind in this hall. And I also declare that the idea also came from this student, PhD student Bhuvaneshwari. The second part of the talk, I'll present to you a concept of anomalous Hall transistor, which is quite different from spin Hall transistor, which is well known. And this work is based on graphene chromium telluride heterostructure. And this work was done by Surabhi Menon. The student is also sitting here in the back of this hall. And I also acknowledge Mandar Deshmukh, who sort of, our interactions with him were very crucial in arriving at this sort of solution and keeping as close to experiment as possible. So let me get started with the first part, sensing vibrations using quantum geometry of electrons. All of us are familiar with Raman, where light is used to listen to vibrations of a system, and there basically the incident light with frequency omega L gets scattered by two sort of into other waves. This is omega L minus omega 0, where omega 0 is the energy of the photon which is emitted, and in this case it's absorbed, you get omega L plus omega 0. Yeah? So by measuring the frequency of scattered light, you can estimate the vibrational frequency in Raman. And Raman, as you know, has been around for 100 years, and it's so omnipresent and powerful, it's used from biomolecular systems to simple and advanced materials everywhere. In this work, we look at rather different type of mechanism, which also can be leading to similar spectroscopy. So you have incident light with a frequency omega L, and phonon with frequency omega 0. And what you see here, unlike Raman, the scattering light will have omega 0 minus to omega L, which is, so in this proposed spectroscopy, basically phonon carries the Stokes and anti-Stokes type frequencies, and in fact, if this we call as G-quase spectra, and if you use it in a circuit model, omega light will be replaced by AC frequency of a circuit operating voltage. And if the frequency of light is larger than, 2 times you can say is larger than the phonon frequency, it becomes basically light related spectroscopy, emissive or radiative spectroscopy. And that is essentially similar to Raman, but the mechanism is in quantum geometry. Yeah? So let me, and this is the paper which basically presents this. Okay, so I'm going to give you sort of a longish intuitive introduction to the quantum geometry to begin with, and that is meant for students and also some experimentalists who may not be familiar with the ideas of quantum geometry. Yeah? So without going through detailed equations, it's possible to learn about it. So let me go back to a very old puzzle that existed, the puzzle of electric polarization. All of you know that electric dipole of a finite system can be readily estimated, particularly if it is neutral. And polarization of a crystal, which is dipole moment per unit cell, is not so simple to estimate. And you will see that if I have a 1D crystal with 2 atoms per unit cell, you will have one direction of polarization if I choose this unit cell, and opposite polarization if I use the other unit cell. And if I use a unit cell which cuts across the atoms, you get basically zero dipole moment. Yeah? So this was a puzzle which existed until 1992, and the dependence of P on choice of unit cell. And this becomes even more tricky when the density is not point charges, but it's a continuous distribution of charge, which is usually the case in a real system. Yeah? So this is the theoretical sort of thinking, but experimentally also the same ideas apply. In fact, if you ask what is measured experimentally, it's typically the difference in polarization, particularly if you have a dielectric sandwiched in a capacitor. What you typically measure is the change in the polarization rather than absolute polarization. Okay, and what I talked about earlier was absolute polarization. So bulk properties usually involve derivatives of P with respect to some external field, and which is why the change in polarization is what we can calculate using any theory, as you will see. So redistribution of electrons within a crystal in response to time varying field is what gives rise to flow of adiabatic current. And if you integrate it out, you will basically get the change in polarization. And this was shown by Rafael Resta in '92. And at the same time, this was my first PhD project with Karin Reb. We showed that actually this quantity is path dependent, meaning it depends on which path if you take a loop path, you can develop what is called as integer quantum polarization. Yeah? This was then, of course, improvised much further by David Vanderbilt and King Smith, who showed that this change in polarization, that integral you can do analytically and show that it's related to what is called as Berry phase in quantum mechanics. It's also linked to Pancharatnam phase, which has origin in Bangalore. This was developed in the context of optical problems. So this is same in quantum context, it's known as Berry phase. And the integrand that you see here is the Berry connection. So most practical calculations of polarization usually involve discretized use of this formula. And in fact, this can be coded basically within a day in most of the DFT or other model Hamiltonian packages. So it's a very practically useful scheme to estimate polarization. So let me now take a little pause and remind you that polarization actually involves flow of electric current, measurement of polarization, and it's linked to geometric phases. That's sort of is the first thing we established so far. And the connection is the Berry phase or geometric phase is also linked to the expectation value of position operator within the occupied electronic state subspace. If you have a two-dimensional system, this becomes more interesting because you can have that integrand, integral along x direction as well as y direction, and you can develop Berry phase gamma x and gamma y in 2D. And once you have that, you can also define basically Berry connection becomes a vector, and Berry curvature is a curl in reciprocal space of Berry connection, and gamma A, alpha basically are the expectation values of x and y operators. Okay, now what happens, this is the key idea behind what is called a shift current, which you have heard about in this conference before. So if you apply electric field along x direction to this 2D system, electron in a semi-classical treatment will move along this direction. But if electron moves along this trajectory, you see the Berry curvature, Berry phase along y direction can change if the Berry curvature is non-zero. Yeah? So as a result, and because this is related to the expectation value of electron in y direction, that will mean electron moves along y direction as the electric field along x direction forces it to, drives it to move along x direction. So this transverse velocity, which is what is responsible for anomalous Hall effect, it's called anomalous because this is coming not from a magnetic field which is present in this 2D system, but it arises essentially from the fact that you have non-zero Berry curvature, which acts as a magnetic field arising from quantum geometry. Okay. So if you have a 2D metal which has a Fermi surface as shown here in the Brillouin zone, which is bounded by this red box, you can show that using Stokes' theorem, if you integrate out the Berry phase along this Fermi loop, you will get basically, you can show it's related to anomalous Hall conductivity was shown by Calculus and others long time ago. Yeah? And phi is the Berry phase in this case. So this is in fact based on the intuitive idea that I developed, that electric field along x direction generates current along y direction because of the non-zero Berry curvature. Yeah? And that's basically the idea that electric field generates Hall current. If you have an insulator in 2 dimension, and then you don't have a Fermi surface, but you can still integrate out the Berry phase along a closed loop, which runs around the Brillouin zone, as shown here. What you can show is it actually gives rise to a Chern number, which is an integer times this 2 pi. And in this case, naturally, the Hall conductivity becomes quantized, given by the Chern number, and it's indeed similar to integer quantum Hall effect, which many of you are familiar with. And this basically means that equivalence between the two edges here and here is broken if Chern number is non-zero, and that basically means time reversal symmetry will have to be broken if you want to have non-zero Chern number as described here. Okay, and the insulator, which has a non-zero Chern number, is called quantum anomalous Hall or Chern insulator. And in fact, consequences of symmetries show you that for spinless systems, the Berry curvature is or under time reversal symmetry in reciprocal space, and it's even under inversion symmetry. So if you have a system which is centrosymmetric and time reversal symmetric, Berry curvature is identically zero, and hence Chern number is zero as well. Of course, you can develop something what is called as Z2 topological insulators introduced by Melee and Kahn. Basically, in this case, the Chern number for upspin electron is 1, and Chern number for downspin electron can be -1. So the total Chern number is 0 as consistent with the time reversal symmetry. But the Z2 invariant, which is the difference between up and downspin Chern numbers, is basically integer quantized. And in the normal insulator, you will see if you look at Berry phase along x direction or position expectation value along x direction, and as a function of ky, it basically is a simple Boring function. Whereas in the topological insulator, it basically traverses from 0 to 2 pi. Yeah? That's basically the one way to think about these ideas, and also the topology which comes in. And these insulators are called as quantum spin Hall or Z2 topological insulators. Okay, all right. So let me now take a pause again and show you that we started out with a simple concept of polarization, which of course was linked to surface charges. As you know, P dot normal vector gives you surface charges. Then we linked it to the current and geometric phase. And now from geometric phase, we introduce Berry curvature, which gives rise to anomalous Hall effect, and also is able to give you idea about topology. And topology basically means you will have edge states, and these edge states are back related to the surface charges in a time-dependent sense. Yeah. So this is sort of the intuitive picture I wanted to develop. And now I'll summarize that in the geometric band theory and the analogy with electromagnetism. The Berry phase is like a Aharonov-Bohm phase. Berry connection is like the vector potential of magnetic field, and Berry curvature is magnetic field strength, and Chern number basically corresponds to Dirac monopole charge, which also comes up when you study Weil semi-metals. Okay, so that's the idea. And again, going back to symmetry, these are quite restrictive. They basically means that any non-magnetic crystals like metal, silicon, which are centrosymmetric, these ideas won't really have any interesting consequences. Yeah, and that limits the class of systems where you can study them. However, in this talk, I will show you that you can really see this in much wider set of systems. So let me go to nonlinear Hall effect now, which has a little weaker restriction of symmetry, being a nonlinear effect. Basically, it's related to the anomalous Hall effect, but in this case, broken time reversal symmetry is needed. In this case, if you apply electric field, the Fermi surface in the semi-classical picture of electronic motion shifts along the direction of electric field, and that introduces the asymmetry in the distribution of electrons in occupying various electronic states in the reciprocal space. And as a result, the first moment of Berry curvature can be non-zero, and there was a theoretical prediction which showed that second-order nonlinear Hall current, Jy, is proportional to Ex squared, so second order in electric field along x direction, times the Berry curvature dipole, which is essentially the first moment of Berry curvature in reciprocal space. Yeah, and this naturally, like nonlinear optics, generates DC current, like rectification, as well as the second harmonic generation in the Hall signal in response to electric field along x direction. Okay, all right. So let me move on. Nonlinear Hall effect has been observed experimentally as well. And the advantage of nonlinear Hall effect as opposed to anomalous Hall effect is, in anomalous Hall effect, you have current at the same frequency which runs along x as well as y direction. So you can measure theta of the current with respect to x-axis to study some of these properties. Whereas in nonlinear Hall effect, there is no current flowing at 2 times the frequency along x direction. So the Hall effect is relatively simple. It has exactly 90-degree angle of the Hall current with respect to, total current at that frequency with respect to applied field. And this was seen in the non-centrosymmetric tungsten telluride in 2019. And indeed, nonlinear Hall effect can be seen even if you have time reversal symmetric systems, but you will notice that to observe nonlinear Hall effect, you need a band gap to be small so that Berry curvature can be non-trivial and large. And second, crystal symmetry needs to be low. Basically, only one mirror reflection symmetry can support some of these features. Here is the calculated Berry curvature and distribution in the 2D plane for tungsten telluride monolayer in the low symmetry structure with only one mirror symmetry. Okay, so nonlinear Hall effect is indeed much easier to access or see in wider classes of systems. But what we show is we don't need to work on, rely on just static symmetries of a system. You can also break symmetry of a system dynamically, like using vibration or other excitations, and that can be actually having consequences. So, for example, phonon is a dynamical excitation, and phonon involves structural distortions which lower the symmetry of the system, which will, through electron-phonon coupling, create changes in Berry curvature, and its first moment can then be measurable. Yeah, that's the key behind our work. So here is a dynamical excitation like a vibration of a system. It lowers the mirror reflection symmetry. In that case, the Berry curvature dipole will also oscillate with the same frequency as the frequency of phonon, omega naught. Yeah, and this will mean you will also, of course, see signatures of this oscillation in the nonlinear Hall current as well, where U is the amplitude of the vibrational mode. You can show in very simple semi-classical analysis that the Hall current has two terms as given here. The first one is basically what was predicted by Liang Fu and Sorrentin, that you have a response, Hall response at 2 times the AC frequency. But which depends on the Berry curvature dipole and restricted by symmetries. But the second one, which is related to the phonon amplitude U naught and this derivative of Berry curvature dipole with respect to phonon amplitude, times there are going to be 3 peaks here. One which comes at omega 0 phonon frequency plus 2 times omega AC, omega 0 minus 2 times omega AC, and one at omega 0 itself. Yeah? So even for a centrosymmetric non-magnetic material, you will see some of these features if the phonon satisfies the selection rule of G-Quest spectroscopy, the selection rule given by basically this derivative to be non-zero. In the later part, you will see it's not so complicated to understand if you remember what Raman does for us. Yeah.
The U is the displacement.
Displacement of atoms in a given phonon. And D is the Berry curvature dipole. That's right.
And this is true for,
you will see it applies to all phonons provided they satisfy this rule. Yeah. So in that sense, it captures the capability of Brillouin, Raman, as well as IR spectroscopies. Yeah. Okay. That's correct. Absolutely, yeah. And also you can work with the anomalous Hall conductivity also, but for the advantage we have for 90-degree angle, we are focused on this at the moment. Okay, so the present work basically is based on first principles theory and simulations. We use DFT, which many of you are familiar with. We obtain electronic structure using this theory, and of course we obtain interatomic interactions, and hence phonons are immediately accessible as well from scratch with essentially no experimental information. So everything I present now are essentially predictions from scratch. Let me first start with the tungsten telluride, the T prime structure, which is non-centrosymmetric. And here I'm showing you 2 phonons which satisfy that selection rule. One is the longitudinal acoustic mode, which involves basically stretching of the lattice along this direction, a y direction, and the optical phonon basically which involves out-of-plane displacements between the 2 sublattices. Yeah? And what we show on the right-hand side is the Berry curvature dipole dxz as a function of strain as well as the phonon displacement. The scales are different, so don't worry that they're overlapping on top of each other. That's just to show that they are linear variations. And indeed, the slope of these curves basically gives you the strength of G-Quest spectroscopy, oscillator strength. Yeah? So this was first principles evidence that indeed you should be able to see these 2 vibrations experimentally. And the frequency of LA phonon is a little tricky because we'll ask which wave vector. And that indeed depends on the size of the sample that you have, and the first sort of fundamental vibration in that strain, it's like basically a macroscopic strain mode, which can be observed using this spectroscopy. Yeah. Yes. Absolutely. Yeah, yeah. Okay. Now, so again, we are proposing here this as a spectroscopy. Lot of people have looked at changes in Berry curvature with strain. Not many by phonons. What we show is any dynamical excitation which lowers symmetry should have this signature. And we develop a spectroscopy based on that.
I do understand, but can I kind of interpret this as not in terms of your final spectroscopic?
Yeah. Yeah, well, electric field, if it changes D, you will see similar effects. In fact, you can have a field effect transistor where gate voltage will modulate the Berry curvature dipole, and you will see this effect. Yes, Greg?
Yeah, can you go back to that previous, yeah, this one here. So I just
Sorry.
want, no,
Yeah.
figure on the right. I want to make sure that I understand. So epsilon y, that's a strain that you're applying?
Along Y direction, yes.
And then the u, that's a displacement of what?
Of this particular phonon, BU phonon.
Okay. And then that, so, and then dxz?
Is the Berry curvature, which okay, in the earlier slide, I probably showed it. Yeah, here, this is dxz.
Okay. All right. Thank you.
Sure. Sorry if I'm going a bit too fast. Yeah. Okay, so how do we, so this is the proof that indeed these two phonons should be GQS active. How do you propose to measure them experimentally? So there are two modes. One is the transport mode, which I show here. This is basically a simple device where this is the channel made up of the material you want to study. You apply electric field, drain to source voltage, and you measure Hall voltage as a function of frequency. Or you can also apply high frequency current, or you have a light which is incident on it, and using antenna structure which sandwich this device, it will emit radiation, which also can be measured as a function of frequency. Yeah? So these are the two spectra we predict from first principles. The first one is the strain mode, the longitudinal acoustic mode that I mentioned. And the beauty is you will see this is 3 gigahertz is basically the central LA phonon frequency, and it's surrounded by Stokes anti-Stokes type frequency changes associated with the operating AC voltage. Second is the BU phonon, which is optical phonon. And that, of course, you will see the central peak is at the phonon frequency, and the side peaks are separated by the operating frequency times 2 times omega AC. Yeah? So indeed, if you change operating frequency, you will be able to make these two wings go away from the central peak. So not only you have a spectroscopic, by just tuning the operating frequency of your device, you can engineer this peak and basically confirm what you are really measuring. Yeah, so it's quite flexible in that sense. In the circuit, you can readily change frequencies. And in this case, we propose to use gigahertz frequency. And that's basically to make sure that the resolution is available to measure those peaks, basically. Okay, so it's similar to IR because the central peak is like infrared peak, but that is for the LA phonon now, you know. The peak is at the frequency of the phonon, and the other two peaks are somewhat similar to Raman spectroscopy. It's also possible to translate signals from gigahertz to terahertz. Our signal was in 1 gigahertz, and now we have a frequency modulation in the terahertz frequency, basically set by the GQS active phonon.
This frequency, the time scale of the phonon.
Yeah.
Its frequency has to be smaller.
Sure, that tricky part, yeah. But the good news is, I mean, the Hall current that we have, it's a shift current. So it doesn't really, the time scale is essentially determined by the transport along X direction in this case.
So the typical, the energy scale of this phone is a terahertz?
Yes, in this case, it's terahertz, about 3 terahertz. Yeah. Depends on the size of the sample. If you have a larger sample, you will have a lower frequency. Varying, G omega, oh yeah, omega AC is the operating frequency. Yeah. It's a function of omega. You will see peaks at 2 omega, sure. Yeah, yeah. It's so sorry. Omega has a subscript which gives you 2 times. Yeah. Okay, so let me move on. At this time, you will still criticize that, well, you have a very nice idea for the spectroscopy, but that may be seen only in quantum materials, which have non-trivial Berry curvature, and that's not so useful, because most materials you have may not be quantum materials with, I mean, in this sense, which have non-trivial quantum geometry given by Berry curvature. However, these ideas are still restrictive. What we now show is we overcome this by learning from surface enhanced Raman scattering, where you use a surface which is quantum active, like graphene. Graphene is a quantum material. So use graphene substrate and deposit another material on it and measure frequencies of that material using the quantum geometry of graphene. So here is an example, HBN, which all of you have probably in your labs, or some of the experimentalists here may have it. So you have bilayer, HBN, and this is graphene. These are the vibrations which we show are G-quase active, meaning if you distort this BN lattice with U, you will see the change in the Berry curvature dipole, which is induced in graphene. So HBN is a large band gap 2D material, which is not at all interesting quantum topology-wise, but in this case, you can use that, induce oscillations in the Berry curvature of graphene and make it measurable. Okay, so the device where you could do this is shown here. The frequency of this terahertz laser is 2.52. This number is chosen because that's where the commercial laser is available. It's not arbitrary choice. And then you measure the basically radiation which is emitted from this graphene. Graphene is a flake, and that radiation, frequency dependent radiation, and you will see the peaks. Basically, this is associated with rectification, and this is associated with the second harmonic solution. Okay, so indeed, yeah. Okay, that's very good question, Anindo. So this analysis is for the aligned HBN, yeah? But that opens up huge possibilities that if you have twist, you will see great richness in the spectra, and the spectra can provide complementary information to what you will study otherwise using various experimental techniques.
I have a question before you go on. I'm not sure I understand to what extent you can get information about the Berry curvature dipole.
No?
Are you able to?
No, so good question, and that's where all referees were stuck, you know. People are looking at it as if we want to study Berry curvature here. That's not the purpose. We want to study vibrations. We are not claiming you study Berry curvature because we are looking at excited states with excitation like a phonon and study the changes in the Berry curvature. So we are not claiming we access Berry curvature or its moments in this work.
Okay, so I mean, is the role of the Berry curvature dipole to give these signatures in the Raman? So the presence, the fact that it's non-zero?
Yeah.
So that's all that really matters here.
No, well, not Berry curvature dipole, but the derivative of Berry curvature dipole with vibrational mode. And only that vibrational mode is G-quase active.
Okay, so you need the non-zero derivative of the Berry
That's right.
curvature dipole.
That's the selection rule.
That's not zero.
Yeah.
That's all you really care about, not
That's
its
right.
size or its...
Yeah. Which is why I said it's applicable to large number of systems. You don't have to have a system with intrinsic non-zero Berry curvature dipole.
Okay.
Or even Berry curvature, like HBN in this case.
Okay, great. Thank you.
Thank you. And thanks for asking questions. I think it helps others in the audience as well. True. Yeah, sure. Okay, but these phenomena are quite robust, okay?
Question to that then. So, I mean, how do you distinguish the mechanisms? Or does it matter to you since you're...
Yeah, well, I mean, second harmonic, you won't see in any other way.
Okay. So these other,
what he's proposing is at a different sort of scale. Sure. Okay, now mechanism in this case basically means changes in Berry curvature and also the Fermi surface, both involve Berry curvature dipole, and they are captured within this single tensor that we define. It's like a Raman tensor, this is G-quase tensor. But same thing applies to all other spectroscopies. Okay, spectroscopies are inverse problem. You go from measured spectrum to vibrational frequencies. It is an inverse problem, and all of us know that inverse is not unique in this case. Okay, so I'm sort of running out of time, so I'm going to rush through the rest of it. We also have quantum sort of picture to understand it, although we haven't worked out the mathematics of the spectroscopies. But essentially, I want to just tell you why it is believable very easily. You all are familiar with the AC, dielectric constant and conductivity. In Raman, you basically focus on epsilon. In this spectroscopy, we are focusing on the conductivity, and particularly Hall conductivity and BCD basically associated with it. So it's not so distant from Raman, but the origin is in really quantum geometry and not polarizability type ideas. Okay, so summarize, I introduced the spectroscopy which can operate in transport and emission modes. It combines the capabilities of these spectroscopies. It can be generalized to other excitations, and it can also be applied to wider set of systems than we believe quantum geometry is relevant in, including 3D systems. Okay, so let me now go to the second topic. I have very little time. This is Surabhi's work, but I'm keen to present it. It's anomalous Hall transistor, and it belongs to engineering heterostructure type of theme of this conference. So the heterostructure we looked at is the graphene and chromium telluride heterostructure. And it's not lattice matched, of course, but the advantage we had is if you use 3x3 graphene supercell and 2x2, they are pretty much matched within 0.5% of strain. So it's, by the way, the idea also came from Surabhi. My students are quite creative, and my job often is essentially to work with them to develop their ideas. So this heterostructure is shown here. Now, why is it so interesting? If you look at the electronic structure of it, the electronic bands of graphene and chromium telluride, which is ferromagnetic, by the way, are essentially shifted in energy with respect to each other. And what it means is there should be electron transfer from graphene to chromium telluride. And that's what we see by looking at the difference in electronic density. This is depletion and accumulation of charges from chromium telluride to graphene. That's the charge transfer. And that gives rise to electric dipole moment, which is perpendicular to the plane, polarization, which couples with electric field you can use using gate FET device. So you can change gate device, induce changes in dipole moment, and that will control the charge transfer between them, and hence carrier concentration. Yeah? So it is really a nice system in that sense, and with a polarization of relatively small value, but it's not that small either. Yeah. So that's the idea, that EZ can control carriers. Now we focus on graphene here, okay, because chromium telluride is ferromagnetic and it exhibits anomalous Hall effect on its own intrinsically, because symmetries allow it to do that. And that's not what we would like to study here. We want to see if engineering a heterostructure can bring in new functional properties. And that's why we first focus on graphene. The Dirac bands of graphene here split up. There is crystal field which comes from the substrate of chromium telluride, which split bands at K and K prime each, and also mixed bands at K and K prime. So you have a mixed sort of valley states at the which fold down to gamma point. And exchange interaction gives rise to splitting of spin degeneracy. So you have 8 bands at gamma point, and splitting due to SOC is much weaker for these bands. Okay, for chromium telluride it's significant, but for these it's very weak, less than a millieV. So you can also write down the 4-band Hamiltonian and do analysis, analytic. The SOC does, yeah. Yeah, it opens up a very special gap. Yeah, in fact, because they, as I said, the bands, all 4 bands mix, and that's the model Hamiltonian which explains. So the bands still remain non-analytic, like a mod of K, and bands from one set of K point mix with the other one to make a Dirac cone here, and then they split up if you use SOC, but by a very small amount. Okay, so first non-trivial functionality is the linear magnetoelectric effect. which is seen in non-centrosymmetric and time reversal broken systems, asymmetry broken systems. And in this case, alpha is about 0.8. And it's calculated by calculating changes in magnetic moment with respect to applied field, which can be readily applied for 2D systems in DFT calculations. And it's much weaker, but it is non-trivial, yeah? And it should be in principle measurable. So it means you can measure changes in conductivity and magnetic moment if you apply field along x direction. And the asymmetry in this curve is basically linked with the fact that Dirac point shifts in an asymmetric way due to asymmetry in the density of states. This is probably the last slide, the anomalous Hall transistor. And this is based on the calculation of Hall conductivity as a function of chemical potential. And what we see is as the chemical potential crosses the Dirac point or split Dirac points, you have a non-zero sigma xy for one spin below for holes and other spins for the electrons. So the Hall voltage that you would see, so it's a spin polarized Hall conductivity, which is switchable by Ez. Ez can change chemical potential along this energy axis. And as a result, you will see that using gate voltage offset by 0.26 volt per angstrom, you can have holes with upspin upspin and electrons with downspin, which give rise to the two distinct Hall signals. And using that, you can now basically measure this Hall signal magnetically by having a magnetic head, or you can measure it electrically by having Hall electrodes to this heterostructure. Yeah, so this functionality, by the way, is not there in graphene to start with. So it's introduced because it is interfacing with this interesting ferromagnetic 2D system. So we get basically magnetically and electrically readable memory device based on this kind of heterostructure. So I'll summarize that there is an emergence of new properties, basically two of them, which are not present in any of the constituent systems to start with by having a heterostructure. And based on that, we proposed anomalous Hall transistor, which is not spin Hall transistor. Spin Hall transistor is based on spin orbit coupling and the separation of spin. What we show here is separation between both charge and spin, which make it electrically and magnetically readable at the same time. I acknowledge my students, Bhuvaneshwari and Surabhi, who did these two projects, and Mandar, whom we have been fortunate to interact with and learn lots of things from. Thank you.
Thank you, Umesh, for a nice talk. The talk is now open for more questions. There were lots during the talk. So, are there any more or? Yes, people want, okay.
Tanushri.
T prime tungsten.
Tungsten telluride, yeah.
But if I had used the TD.
Yeah. We have done all the three structure, T prime and TD. It's in the supplementary information of that paper.
So in the TD, if I use,
yeah,
of course with a different symmetry now,
yeah,
do I be able to really engineer similar kind of spectroscopic tools?
Yes, yes.
I see.
Well, I mean, the specific phonons and their frequencies are a bit different, but yeah, we have shown details of that in the paper. Thank you. Okay, I see. That's right.
Or some specific line symmetry which makes the derivative of B vanish.
Okay. That's right. Thank you. Yeah, we are hoping to work with Amit. He's the theory expert in twisted systems, and we really think these will have spectacular consequences in twisted multi-layer systems.
Okay. If there are no more questions, we thank Umesh again.
Thank you.